G'day. Copy the heading down and then we'll do some hard yakka. We will start by testing your knowledge, so put down the numbers 1 to 10 under your heading. One. Greek philosophers Leucippus and Democritus imagined atoms to consist of small, indestructible what? Two. Which element that makes up most of our Sun has the smallest atoms? Three. Name the yellow non-metal element that used to be called brimstone. Four. Which element has 8 protons in its nucleus? Five. Dmitry Ivanovich Mendeleev invented what table with 8 columns? Six. What do we call the centre of an atom where protons and neutrons reside? Seven. The heaviest naturally occurring element is element number 92. It is used in the armour of this American tank and is slightly radioactive. What is its name? Eight. What is the approximate size of a hydrogen atom in metres? Is it 1/10,000th, 1/10,000,000th, or 1/10,000,000,000th? Nine. This is the formula for ozone that protects us from ultraviolet radiation. It has 3 oxygen atoms in the ozone molecule. Is ozone an element or compound? Ten. The elements of group 8 are usually called the what gases? Make a side heading in your book, Metal Facts. One of the joys of life is to visit the high country above the snow line. This picture shows the mountains on the border between Austria and Italy. The Otztal Alps, as they are called, contain the melting remains of an ancient glacier. My brother-in-law has just survived a blizzard up there and seems to enjoy walking around for weeks on his own. On the 19th of September 1991, 2 German tourists found the mummified remains of a body sticking out of the glacier. The Iceman Otzi died violently from an arrow to the back and a blow to the head around 3300 BC. He was well equipped with warm clothing, a fur hat and a range of tools and weapons that he had used. His flint dagger is to be expected. Flint is very sharp and harder than steel, not unlike these tools found at Port Stephens. However, the axe is interesting. It has a 2-foot handle made of yew timber and ends with a 4-inch blade of almost pure copper. Hair analysis reveals that Otzi was involved with metal workers. His hair contains the arsenic and copper that you would expect from people who heated copper nuggets to over 1100 degrees Celsius in ceramic pots using bellows. The Copper or Chalcolithic age marked the beginnings of metallurgy. It was not based on metal ore compounds, but in melting and working native copper. This happened in Iraq as early as 8700 BC, and even in the Great Lakes of America in 4000 BC. Ancient metal workers such as Otzi were among the true pioneers of chemistry. They were experimental scientists who learned by trial and error to extract metals from rocks. They lived at a time when writing was little more than scratchings on clay tablets or pictures on a wall, and few could read it or even wanted to. Metals were very useful things to have. You could heat them and pound them into all sorts of shapes, like metal spikes, metal rings, shoes for old Dob and the horse, or ploughs for the farm. Or you could find yourself a good grindstone like these ones and put a nice edge on a pair of shears. Then you could do the Aussie thing and grab a sheet with your mates and sing an old Aussie song. The history of civilization was closely linked to the discoveries of the metalsmiths. After working with pure copper nuggets, they began to use bigger and hotter furnaces with lots of charcoal and bellows to fan the flames. They learned to extract copper from a variety of ore minerals: azurite, malachite, and finally chalcopyrite. This corroded ancient copper ingot came from Crete. By 3000 BC, the metalsmiths were combining the copper with tin to make bronze. One source of tin was Cornwall in southwest England. This is Tintagel Castle, the legendary home of King Arthur. And these bronze castings came from Somerset in England. This Bronze Age sword came from France. The Iron Age replaced the Bronze Age around 1200 BC. The first iron dropped down from the sky as meteorites such as this one. Extracting iron needs a lot more heat than bronze. The addition of carbon makes the iron harder and it can be more easily sharpened. So copy this information down into your books. Maybe it's time for another hero. Danish scientists Niels and Harald Bohr played soccer together in the combined university's team, Akademisk Boldklub. Niels was goalie. Harald went on to be selected for the Danish national team. This is a photo of the Olympic silver medalist soccer team of 1908, and the young man on the right with lots of attitude is young Harald. Niels went on to Cambridge and trained under New Zealand physicist Ernest Rutherford. His work won him the Nobel Prize, and he became every bit as prominent in physics as Einstein. Copy down Bohr's discovery about element atoms. Unreactive inert gases have full outer shells. This is argon, which makes up 1% of the air we breathe. Write down the total number of electrons in each shell, counting from the inside out. The most important part of an atom is its outer electron shell. This determines its chemistry. We call the outer shell the valence shell. In argon, the outer valence shell is full, causing it to be unreactive. So it belongs to the unreactive column 8 of the periodic table, which we call the inert or noble gases. All other elements in the periodic table are under tension. They want a full outer shell, so they will lose, share or gain electrons using other atoms to gain their objective. If they have a small number of valence electrons, they will lose them to another atom. If their outer shell is half full, they will share with another atom. But if the valence shell is nearly full, they will grab electrons from whatever other atom is available. This is silver, element 47 in the periodic table. It has just one electron in its outer shell. It is a typical metal, but like all elements, desires a full outer shell to be stable. So do you think silver will lose its electron, share its electron with others, or gain electrons to fulfill its need? So complete and copy our third metal fact, shown in yellow. The answer is that the big fat silver atoms easily lose their valence electrons to achieve a full outer shell of 18. All metals are electron losers. But this is the great property of metals. In a crystal of metal, the valence electrons wander through the metal lattice. Metallic crystals are held together by an attraction between the positive metal ions and the negative wandering electrons. This explains how metals are different from non-metals. First, metals are good conductors of electricity. When we apply a voltage across a metal, the tiny negative charges are so easy to push from the negative to the positive. We use a lot of copper wire for the purpose of transmitting electricity. So copy this important metal property. Heat in materials is related to particle vibration. When you heat a metal, the valence electrons are tiny little fellas and easy to move. At normal temperatures, they can be wiggling at 1,000 kilometers per second. So you have to be very careful when handling hot metal. This table shows 4 different conductivities in MKS units. You might like to explain why expensive stainless steel saucepans have a plastic handle and a copper bottom. The steel is a reasonable conductor of heat and very easy to clean. The plastic handle is an insulator, so your hands are protected. The copper bottom allows the pan to heat quickly and save on energy. The next property of metals is that you can cast them into shapes. All you need is hot metal in a ladle and moulds containing the shapes that you want. Here we have a big iron ladle, a casting pit, then we just pour the liquid metal into the mould. So copy down these 2 properties. If you look at this diagram of a metal crystal, you can see that you can move whole sections of atoms without changing the structure of the crystal. So metals can be hammered into shapes without breaking them. Diamonds are hard but can be shattered with something big. Non-metals are not malleable. Metals are malleable and can be beaten into shapes by blacksmiths or using big metal forges. Rolling mills do much the same thing. This is hot rolled coil, and this is a small brass sheet rolling mill. The most malleable metal is gold, which can be rolled to very thin gold leaf, which is used to gild painting frames. A related property of metals is that they are ductile. You can drag a wire through tiny toughened openings and reduce their diameter to the gauge that you want. These are toughened draw plates, and these are some wire mills. Alloys are essentially mixtures of metals with other elements. The atomic structures of the metals are altered, changing many properties such as hardness, appearance, malleability, and resistance to corrosion. Alloys are not chemical compounds with a definite chemical formula. They do not have sharp melting points because they are mixtures. When you mix molten copper and zinc together, you obtain a number of brass alloys that look nice and resist corrosion. Most coins are alloys, and our silver coins have changed with time. They started off being almost pure silver, and now are an alloy of copper and nickel. Perhaps we should look at the periodic table to find where the metals are. There are an awful lot of them here. The non-metals are shown on the right in green, and there are only 10 of them. The noble gases in blue are also not metals. The metalloids or semi-metals in khaki form a dividing line between the metals and non-metals. They have some metallic and some non-metallic properties. But there is a trend here. Metals are on the left as they have smaller numbers of valence electrons. Fat atoms at the bottom of a group tend to be metals as their valence electrons are more easily lost. Something for you to write down. Next we will visit some famous metals. Draw up a table like this one and make it the width of your page. The most dangerous of the metals are those of group 1 of the periodic table, shown in red. We call them the alkaline metals. They are lithium, sodium, potassium, rubidium, cesium and francium. We never find them free in nature. If they did, the rocks would explode when it rained. The most common of these elements are sodium and potassium, which form the stable salt compounds which allow our body cells and brain cells to work. So write down sodium in your left column. In your right column, as I talk about sodium, you can write some keywords to describe it. Sodium has been given the unusual symbol Na, which is derived from the Latin word natrium. It is a soft grain metal, melts easily, and is usually kept under oil to keep it from reacting. Its most common chemical compound is the sea salt sodium chloride that is crystallising in the satellite photo of Lake Eyre. Sodium was first extracted from another of its chemicals, sodium hydroxide, by the man from Penzance, Cornwall, Sir Humphrey Davy. He used the power of his humongous-sized battery to drive electricity through the molten chemical in a furnace like this one. Davy was fascinated by its reaction with water and its yellow light in flames. Davy discovered and played with some of the most dangerous elements. His eye was injured in an explosion and he died young from lung damage. Sodium is called an alkaline metal because of its reaction with water. It gets hot, melts to a molten blob, makes hydrogen gas and floats. Then it produces the dangerous caustic alkali, sodium hydroxide, which in this picture is turning the indicator pink. Then the hydrogen explodes, and if you get hit in the eye with a molten metal, it will catch fire and burn into your eyeball. This is why we always wear goggles. The sodium vapour produced in the explosion is not kind to your lungs either, and alkali burns are painful and slow to heal. All the alkali metals react in this way with water. Before I move on, I want to deal with the issue of laboratory safety. Australia's wartime generation well knew the horrors of explosives. 1 million of our citizens wore the uniform, and there were 7 million dead in the Pacific War, most of them civilians and tortured prisoners of war. This family photograph shows what happened when someone did the wrong thing in training. They shoveled the bits of the young soldiers into coffins. People are killed or injured when some lunatic surrounds a vigorous reaction with a hard container such as glass. Never do this in a laboratory or particularly outside school. The shrapnel can go right through you. There have been horrible injuries and deaths among the careless. Always wear safety goggles and clean up chemical spills when you do an experiment. I hope you get to experiment in safety with lots of chemicals. I certainly did. Science is meant to involve fun and hands-on pracs. Bunsen burners and equipment are truly wonderful things. While sodium is extremely dangerous in element form, its compounds have found many uses for thousands of years. So put this sentence in your second column, then you can list sodium chemicals and their uses as we come to them. All living things contain salty water, which is necessary for their living processes. The main salt is also dominant in the sea and is called sodium chloride. Most animals, including us, have a taste for it, although too much causes harm. Salt crystals form by evaporation of seawater. We harvest a lot of salt in South Australia. It is used as a food preservative with corned beef and as a saline solution to feed sick patients with sugars intravenously. Another ancient chemical is sodium carbonate. It was first produced from natural minerals in nasty desert places or by burning seaweed and collecting the ash. Its original use was in glass making with sand. In the home we call it carb soda or washing soda, and it can be used to scrub mould off shower recesses or as an environmentally friendly mild detergent for removing stains. It is also a water softener in bull water areas. Bread and cakes are tasty because they are pumped up with carbon dioxide gas. This is unleavened bread, used by Jewish people to celebrate their survival at Passover. It is quite tough to eat. The ancients learned that the best way to make bread is to add to the dough a microscopic organism called yeast, which eats some of the sugars and starches and blurts out carbon dioxide. This is dried yeast, and this is what yeast looks like under a microscope. Add it to the dough and it will rise to form a bread full of tasty carbon dioxide bubbles. Sodium bicarbonate or bicarb soda is a modern chemical replacement for yeast. It is a very mild alkali and will react with natural acids in the food to make the carbon dioxide chemically. It is sold pure or as ingredients in baking powder, self-raising flour, or in antacid chemicals for the temporary relief of indigestion pain. Our ancestors were rather ugly, quarrelsome, and smelt pretty bad until someone discovered how to make soap. Australia's pioneering women worked very hard, and one of their tough jobs was making crude hard soap using lye, which they purchased, and beef fat left over from cooking meat. Lye is caustic soda or sodium hydroxide. Caustic means that it can burn all parts of your body, including skin and eyes, so keep it well away from the kiddies. Caustic soda can be used to strip varnish off furniture and is a key ingredient in Drano for unblocking drains. Caustic soda is also used in oven cleaners, so wear goggles, gloves, and don't wipe your face. Our next alkali metal is potassium. So rule off after sodium in your table, write potassium down in your left column and its symbol and Latin name in your right column. Like sodium, potassium is soft and grey and easily cut with a knife. It has a low melting point. It is very dangerous and will explode with water, forming potassium hydroxide alkali and hydrogen gas. The flame colour of its salts in a Bunsen burner is a pretty lilac. You might be wondering how the name potassium came to be used for this very important element of life. Well, it all began with man's obsession with wood. We Aussies lost little time in cutting down the hardwood forests. Many of the woodcutters were Scots and there are few trees left in Scotland. Over in the land of the free they were doing similar things to their hardwood forests. This particular timber is Oregon. The old-timers found that when wood is burned in pots, the pot ends up full of a white ash called potash. This alkali could be processed into its pure form called potassium carbonate. This chemical found several uses for glass making, soft soap making and fertilisers. The potato farming Irish knew that the best way to grow their pretters was to roll the seed spuds in wood ashes before planting. This made them rich in potassium salts that humans need. It worked very well until at least one potato disease spread from America beginning in 1841. The Great Irish Famine killed 1/4 of the population and caused many survivors to emigrate to Australia. 1 million dead still leaves a traumatic legacy on the thrifty Irish. Fertile soils, particularly in an arid country like Australia, are most necessary for human survival. Potassium in soils is formed by the chemical weathering of feldspar minerals, which are found in a number of igneous rocks such as granite. Australia has not formed new igneous rocks in the recent past, so our soils are deficient in potassium in many places. Good artificial fertilisers contain potassium, usually in the form of potassium sulphate crystals. We obtain our potassium from the fruit, vegetables and meats that we eat. It is one of the salts needed for our body cells to function and for our nerve cells to process electrical signals. In our next video, we will visit some more important metals. Until then, cheerio.